Hey, Mzenzi Coders, how's it going, guys? So today actually we're going to be looking at Min-Heap. So Min-Heap is one of the efficient data structures that we have, especially for getting some sort of like kth largest element or getting some sort of like kth element in a given array or something like that. So it's gonna like motivate you why sometimes you might want to use a Min-Heap. For example, let's say you're given an array whereby you have values such as 1, let's say 4, 1, 2, 5, 3, right? And you're given that you need to get the kth element, right? You need to get kth element. So let's say, for example, in our example, we can say get the second largest element, right? So how will you do this? Probably one way we can think about is this, that okay, we can sort this, right? We can say 1, 2, 3, 4, and 5. Now that we have sorted this, it can be easy. Starting at the end, can say 1 and 2. So we know that okay, the second largest element in the array is going to be 4. But this comes at the cost of time complexity, right? It's not necessarily a bad solution. It's just that there's a better way to do it. For example, this solution that we came up with, it's going to take n log n because we're sorting, and it's going to take another n because we need to traverse the array to kind of like get the kth element again after we've sorted it. And this is where the Min-Heap guys comes in to kind of like beat this time complexity, which it can do with k log n. How is that so? So the properties of Min-Heap, it's more like a complete binary search tree, whereby in this case, because we're working with Min-Heap, so all the subsequent node will be less than the root or their parent. So for example, here we have 3 and here we have 9, here we have 20, so 15, 19, 41. So all these, as you can see, are decreasing. All of these in the values will be small. So why is this important? Let's say now you wanted to get the smallest element, right? You wanted to get the smallest element in the array. This will be, you can just get this. You can just take this to kind of like grab or extract an element. You can do that with constant time. So you can just get it, then you're going to heapify. So for example, to get 3, you can just get 3, then you have to bring 20 here. Then as you bring 20 here, then you're going to apply another concept called heapify, whereby you just need to adjust these values back again. For example, let's say you have 20 here, you're just going to look at 9 and 7 because you're looking for the smallest value, then which means that you're going to bring 7 here, then 20 will come here, then here will be gone. So you're going to end up having something like 7, 9, and 20. So what we just did was that we extracted 7, but we still had to apply a heapify, which is log n. So, and for the kth time, meaning that if like we had to do that to get like the second largest number or something like that, or the smallest largest number at the specific k time, we'll traverse that again. But I hope that makes sense. If it didn't, it's okay. I will explain this in more detail, and you will actually be able to understand everything. Trust me. I've realized that people learn. Some people learn very well when they can see the visual at the same time they can see the code. So we're going to use this as our visualization. As I explain the code, we're going to be manipulating it. So you can think of this as a tree. So how do we store these values, our data, in a programming way? So we store them in a list. So for example, this is how we store them. We start with 5, we start with 10, 11, we start with 40, just like that, right? So that means we're going to have something like 5, 10, 11, 40. And this is how we store them, okay? So we're going to start by initializing our variables that are going to be important to us. So we're going to have a Min-Heap whereby we initializing some of the variables. So some of the variables could be that we need to have a max size. So the max size essentially is going to say all the values that you add to your array, they mustn't surpass the max size that has been set. So you can think of this as an array that is predefined. So we're going to have self.max size equals to max. So as we insert, this is going to become crucial on the function of insert. Sorry about this. I think I didn't tell you all the functions that we're going to have. So let me just write them here. We're going to have the insert, and we're going to have the print function just to show the values, and we're going to have the extract, and we're going to have the heapify that explain that when you extract the top value, the minimum value at the top, what you need to do is that you need to extract the last value and put it at the top, then heapify, meaning that adjust it until you kind of like have that min-heap properties. So you need to maintain the min-heap properties every time. So what I'm saying here is that I'm going to explain this anyway, but let's just continue. So we have self.max size equals to max size. Then we're going to have self.size. So I need to maintain the size of the min-heap. It's going to be important as we insert and extract. So another thing is that I'm gonna need a helper function, guys, is that mainly because I want the start in the array. I want to add a dummy value, so we can maybe make this like 1 million or something like that. This is just going to help us that every time we have some operations to get the second value in the heap, we can get it much easier. If we didn't have a value here, then we were not going to get it that easier. So this is just a dummy value that we have, but as we go along, you will understand the significance of this value here. But just know that I need that value. So which means that I'm just gonna take the heap, and we're gonna say heap equals to first value, we're gonna multiply it by self.max size plus 1. Then we're gonna, because here I'm just creating a heap based on the based on the max size, so this is just going to make sure that my heap has all the elements. So let me show you what this does in Python. So let's say we have 0 and I multiply it by 5. It's just going to give me 5 zeros. So what I'm doing here is that you can think of, if they said that the max value was supposed to be 10, you can think of me just saying 0 times 10. So this is just to make sure that I'm initializing my heap with all of those values. Then I'm gonna replace them as we go on. Then I'm just gonna say max self.heap, which is the values at the zeros index. It's going to be sys.max size. Just imported the system, so it's just gonna be just the dummy value that I was explaining you about, guys. So it's gonna be system. Then what we do is that this is where we kind of like try to get some of the helper functions, but I need to explain this helper function so that you guys can actually understand what these helper functions does. So sometimes we're gonna need to get a parent, especially when you extract, right? Or you insert. So let's say you wanna probably insert a value. Let's say that value that you wanna insert is something like 50, right? Let's say you're inserting, actually let me say 2 so that you can understand. So you're inserting 2. By inserting 2, you can see that you're already breaking the heapify, the min-heap properties, because this is not a small value. It's supposed to be here. So what do you do in this case is that you need to check the parent 10. You need to check it. How can you then check the parent? How do we get that 10, right? So what we do is that we need to have a helper function then to say get a parent, because when I'm going to insert a value at the end, and this is how we insert, by the way guys, we insert here, that 2 will become here. This is where it's gonna go. It's gonna come here, and this is how in the tree, this is how it looks like. It's gonna come here, right? We inserted it here, but as we insert, we want to see its parent, right? We want to see its parent. So I hope you guys kind of like get an idea. So that's why we need a helper function to get the parent. So how do we get the parent? To get the parent, I'm just going to create a function whereby it's going to take the self, it's going to take the position, and we're going to say return the parent, which you take the position and you divide it by, you modulate it by 2, right? I want to explain this, how this works. So let's say we have 0, we have 1, we have 2, we have 3, 4, we have 5. Okay, so what we do is that we take the values position that we just added, which is 5, and we modulate it by the what did I say on the function? We take the position, we modulate by 2, right? So you're gonna take 5. Let's do that. I want us to do that because we're adding 2, so it's on the position 5. We modulate it by 2. What do we get? We get 2. 2. What is 2? 2 is 10. Perfect. Can you see that it works? So we're gonna get 10. So this is why, this is how you get your parent. So even for 10, you want to get the parent of 10 as 5, you can do the same thing. You can go to 2, you're gonna say 2 modular 2, you're gonna take 2 and you modulate it by 2, then you're gonna get your parent. But this is how you get a parent. Okay, so I hope that kind of like gives you a perspective about all of these helper functions that I'm writing, and they're not actually confusing. So this is how we get a parent, and now we need to have another helper functions, guys. So all of these helper functions, you will understand them as we go along, but I'm trying to, by all means, by as we're writing them, you understand them. So we need a helper function to get the left child. So how do we get the left child? Remember that when I said extract, when I showed you in the visualization, I said at some point we need to as if like we want to extract what is it, we want to extract 5. Like let's say this is just an example, we want to remove 5, we're gonna remove it, and we're gonna take let me remove this 2 because it was just an example. We want to remove 5, and we're gonna take 40, we're gonna bring it here. So 40 is gonna come here, right? Like we spoke about this. 40 is gonna come there, but when 40 comes here, what you want to do is that, because this, you can see that this is not a min heap because the values here are less, so you need to do something about this. You need to take 40 and bring it below. How do you then do that? You need to look at your left child and your right child. But how do you then look at your left child and your right child? How do you do something like that? And this is where the left function is going to come in. So the left function is going to be def left child. We're going to take the self and we're going to take position. So we're going to return 2 multiplied by position. So why are we doing it this way? So let's go to the example again. So remember that we want to get the left child of every parent. For example, here 5, given 5, what is the position of 5? It's 1, right? So we can say, we said the function is, the formula is going to be 2 times what? It's going to be 2 times, what is the position of 5? It's 1. So by 1. So if I do this, I'm supposed to get 2. Yes, I get 2, which is the left child of 5, which is 10. It makes sense. Can we get the left child of 10? The left child of 10 is 40. So what is the position of 10? It is 2. So I'm just going to write 2 here. 2 multiplied by 2. I'm supposed to get 4 because that's where the left child is lying. So we're just going to run this. which is 4. So that's correct. So that's how we get a left child, right? Now we're gonna look at getting right child. And like I said, guys, don't forget that the reason we're doing this is because every time we extract the value and we add a new value at the top, we need to look at the left and right child if they are greater, if they are smaller than the current root. Because if they are not, we need to adjust them. So that's why these two functions are quite important also. So we're gonna say right child, okay, and we take the self, we take the position, then we're just gonna return 2 multiplied by position, and we're gonna add bright 2. Okay, cool. With these functions out of the way, now we can actually build our mix heap. Let's not forget that the mix heap function is just to say, if we extract the value at the top, the smallest value which is at the top, we just want to adjust and take the last element and put it at the top and adjust it, so that we keep the mean heap properties intact all the time. Okay, so that's the purpose of mix heap. Mix heapify, I meant to say. Actually, I think Min-Heap. I always intangibly make mistake with these two concepts. So we say if the position is not a leaf, so now I see that we're gonna, because remember that we need to check this, we need to check 5 and check all the subsequent nodes to check if these nodes are less than or greater than 5, so that we can make a necessary adjustment. But imagine if this 5 was a leaf, meaning it was at the end, then we wouldn't be able to check the subsequent node. So hence it's important that we have a function to check if a value is a leaf. So which means that before we start, we're going to have another function which we call def is leaf. So this function essentially is going to take the position, and what it's going to do is that it's going to check if the current position is greater than self.size modular 2, and position is actually less than or equals to self.size. So we return true. Then we know that these properties matches that it's a leaf. So we're just gonna make sure that we cover this, make it cleaner. So we check if the current position is greater or equals to the size modular by 2. Then we check that if the position is actually less than or equals to the size, and that is going to give us the leaf. So you can actually try to take this, and you'll see that it actually works. And you try to do it on that array, on that small array that we have, and you'll see that actually it works. So what we do is that we say if not, because we know that if it's a leaf, it's going to return true. So we say if not true, self.leaf. Then if it's not a leaf, then we just want to say obviously given the position, then we just want to heapify. Then how we're going to do that is that we just have to have another check. Remember that the second check is to check if, because of this is a min heap, so if we have 5 here, we want to check if these values are smaller or greater. For example, if we were about to remove 40, right? If we extracted 5, we're going to bring 40 here. So the first thing that 40 will do, it will check if are these guys smaller than me, right? If they are, then obviously I need to adjust them and bring them at the top, because this is min heap. So that means we need that check to say, okay, if self.heap position, right, the position that is given, it is greater than self.heap then we're gonna take self dot left child, because we had that function which is left child, which is also, I think it's position. Then so what we're saying here is that given the position, which is, we can think of this as 40, if it is greater than the left child, which is 10, then we want to do something, and we're going to have an or statement to say, or if self dot heap position, so if any of the right or left are actually less than the position, then we want to heapify. So here we're just going to say position is greater than self dot heap, then we take self dot right child, then we're going to take the position. I think this is how it works. Hope we didn't have an error. So what did we just do? We checked if the position, it is actually greater than the left or right child, because this is min heap, we have to adjust them. So how do we then adjust them? So we adjust them by checking the left if it's less than the right. So what I mean is that because we brought 40 here, we checked these two if are less. We did check them and we saw that actually they are less than 40. So what we do is that we check if left is actually less than right. So if that's the case, what we do is that we swap these two. We swap this position and this position, and we swap, like the left 10 is gonna come probably here, just write it down, and 40 is gonna come here. Okay, so that's what we do. So kind of like give you a better perspective, let me show you from the code. So we're gonna say if self dot heap, then we check if self dot left child, I think, then we take the position. Okay, we say if this is less, you can think of this 10, asking 10 is less than self dot heap, then we're gonna say self dot right child position. If this is the case, then we want to swap them, but I think it will be a good idea to kind of like have a function to swap. Okay guys, so what we can do is that we can scroll up, we can scroll to the right, then what we can do is that we can actually create a function to swap. So we can say def swap. So if we're given two position, pos 1 and pos, what is it, pos 2, ne? We can actually swap this. We're gonna say self dot heap take pos 1 and equals to self dot heap, and this is gonna be pos 2, and we're gonna say equals to, actually now I'm just gonna copy this to save my time. Gonna be self pos, and this is gonna be self pos. So I'm just swapping. This is how you do it in Python. You just do it in one liner and it's more efficient, and that's it. So now we're going to use the swapping function that we just created. We're gonna say swap the position with self dot left child position. So we're literally swapping these two, and this code will do the trick. But after we swap them, I want you guys to understand that we still need to apply the min heapify, and mainly this is because let me just show you guys, but let me explain to you. So we did a good job we swapped 10 and 40. But imagine if we had values here, something like let's say we had 13 here, right? We can see that 40 is actually greater than 13, which is not meeting the Min-Heap properties. We know that 13 should be here and 40 should be still come here, right? What does this mean? It means that we need to call the Min-Heap again. We need to heapify until 40 gets to the leaf. Or even if 40 was here, and we had a greater value here, like something like 50, then it will be fine. It will be totally fine. We don't have to do anything because the Min-Heap properties are satisfied. But now, like I said, if we have 13, then we need to, because of now this is breaking the Min-Heap. So what does this mean? It means that here we just need to say self dot min. After we swap them, just need to say min heapify. So we're just calling the same function, guys, right? So just gonna say min heapify, take where the left child was, self dot left child, because position, and apply the Min-Heap. So we had an if else statement to check if position left is less than, because we want to start at the left, but if this is not true, then we're going to start at the right. So which means that we're going, what am I saying? What do I mean by right? I mean, remember that we did check, let me just revert back. We did check that for example, we said 40, 10, 11. So we did check if like left is less than right. However, if this is not true, what we want to do is that we want to, let's say here it was 12. So what we want to do is that we want to swap 40 with 11. So we're just going to bring 40 here, we take 11 here, right? So if it happens that this 12 is not less than right, then we're just going to take the right. So that's why we have else here. So we're just going to do the same thing. Actually, I think it's fine if we copy and paste, because we're just going to say swap the position, but instead of the right child, we're just going to say right child, and take the right child position and apply the Min-Heapify, and that's it. I hope you guys kind of like understand. I feel like if you don't understand at this point, as long as I try my best to explain it this way, it's hard to memorize this code. So I'll say like just like write it yourself, and like then you will get used to it and you will understand actually how the Min-Heap works, or Max-Heap. Now that we're done with the Min-Heapify, let's look at the insert function. So here we can think of like we are given an element. Now it can be an element. We want to insert it, but before we insert, you still remember when we started, we said we can have a constraint whereby we are told that our data structure is not supposed to exceed, meaning that the size is not supposed to be greater than or equals to self.max size, right? If it happens that it's greater than that, we just need to return, meaning that we can insert. We are occupied. So, however, if we still have space, what we can do is that we can take the self.size. We can say, okay, add by 1, can increment it by 1. We can add. Then we're gonna add that element at the end because of that size. So we're gonna have heap take the last element, which is size, is gonna be equals to element, something like this. So what I just did here is that you can think of it as we have an array of 1, 2, 3. Then we're saying we want to add 10, right? I'm just saying add 10. That's it. So that's what we did. I think here I just need to say self.size and it should work. Perfect. So we're just gonna say current because we want to update this self.size. Before I get into the subsequent code, I want to explain how do we actually insert, so that as I write this code, you can actually visualize it also in a break. So let's say we have this Min-Heap, right? It meets the properties of a Min-Heap. It's perfect. And we want to add this 2 here. We want to add it here. Actually, let's not make an example with 2. Let's make it with the big value. Let me say we want to add, actually 2. Yeah, it's fine because this is a Min-Heap. So we want to add 2. So if we add 2, you can see that the Min-Heap properties are broken, because we know that this is supposed to be decreasing, meaning that it's supposed to be small, then these values are supposed to be larger than this, then these values are supposed to be larger than all of this, but now we have 2 here. So we need to adjust this 2 and get it at the top, right? We need to swap it with 10, come again, swap it with 5, and do that. So which means that for us to do that, we need to compare 2 with the parent. Does that make sense? So we need to say, is 2 less than the parent? That's the code that we're gonna write. And if it is, then we swap them, meaning that 2 is gonna come here and 10 is gonna come here. We ask again, because it's a while loop, we ask again, is 2 less than the parent? Yes, it is. Then we take 5, we bring it here. Then we take 2, we bring it here. Now the Min-Heap properties applies. This is not bad. I think we're gonna do that, and we'll see how it works. So what we're gonna do is that we're gonna say while self.heap, then we take the current. I think here I'm supposed to current. So here I'm saying self.heap the current value if it is actually less than self.heap dot self.parent. We had a function to get the parent of the current value. I think here I made a small bug. So if the current value 2, as in our example, is less than the parent, then we wanna do something about this, meaning we wanna swap them. So we're gonna say self.swap the current with self.parent of the current, right? Then when we're done, we just want to update the current because the parent of the parent might be greater, so we just want to make sure that we updating this. So we're gonna say current is gonna be self.parent of current index. Okay guys, so we're gonna write our last function, which is going to be extract. So you can think of this function as we kind of like taking the smallest value in the array, because the smallest value is always going to be at the top of the tree. So we can do that by saying, actually let me declare a variable, because we know that this value is going to be sitting at self.front equals to 1. Then we just gonna say popped equals to self.heap self.front. Okay, so we gain the last element, and I'm just gonna say self dot, meaning that I'm gonna take the last element and overwrite it. So by what I'm saying here is that I'm gonna take self.front, the first element, and I'm gonna overwrite it by the last element in our array. So it's gonna be self.heap self dot size, because it's going to be the last element. Then which means that because now I have removed the first element, I've overwritten it. So what I need to do is that I need to then decrement the size. So it's going to be equals to -1. But remember that because I've removed the first value, I could have replaced, obviously I've replaced it with the larger value. So what I need to do is that I need to adjust it. So which means that I'm going to say self dot max, what is it, Min-Heap, right? Min-Heap phi. Okay, there's it. Self dot front means that I think I made a silly mistake. So what we're doing here is that we're saying take the first element, so which means that we're gonna be having something like this. Let's say we had 1, 2, 3, right? So we pop in the first element, meaning that we're removing 3, we're removing 1, so we're gonna be left with 2 and 3. Then we say overwrite the front position, meaning the 0 element with the size. So where 1 was, it's gonna be 3, so we're gonna be having 3 here. Okay, then what we're gonna do is that we're gonna apply the Min-Heap, meaning that we're gonna say, okay, 3 is here, but 3 is not a minimum value, so we need to remove it. So we're gonna apply that, then 2 is gonna come here, then we're gonna have something like 3. I hope I'm not confusing you guys. I hope you guys got the concept and what I'm trying to explain now. I hope it kind of like flows much easier. Yeah, I just hope that's the case. So actually here it's gonna be 1, then it's gonna be self Min-Heap self front, then we can return the popped value, right? And I think that will be it, guys. So you can check the question on Ninja website. You can copy and paste the code, but in this case you're just gonna need an insert and the print function. You can also check the solution from Geeks for Geeks. Check they kind of like wrote it very well. If like my explanation didn't make sense, so you can check their website. You can also go to LeetCode and search for Min-Heap equation. You will get it, and kind of like right there. So I think that will do it, guys. Thank you very much for tuning in. The main goal here was to kind of like explain Min-Heap to you guys. I think the concept applies the same to Max-Heap. You're just gonna change these signs, less than, greater than. That's the only thing that you're gonna do, but other than that, they are the same. Thank you guys. See you in the next video.